Is Mr. Wise. Today we're talking about energy reactions. We have exothermic reactions and endothermic reactions. Let's start with the root word here is therm. Right in the middle, you see THERM, that's therm. Therm refers to heat energy. And anytime you have this suffix ic, it means pertaining to. So pertaining to heat energy. Now we have two prefixes, one exo and one endo. Let's start with exo. Exo, like in the word exit, refers to going out. So when we put that all together, heat energy is going out of the system. So the system in this case is the chemical reaction, the reactants and the products that are happening here, and energy is going out or being released. So the definition of an exothermic reaction is a reaction in which energy is released during the reaction. And if you look at this graph, on the x-axis, we have over here on the left the reactants. Right in the middle, it says the reaction progress. And on the right, it lists the products. So this is basically time in the reaction, where we start with the reactants, we combine them to create the reaction, and then the reaction goes on and we're left with the products. And so the energy on the y-axis here is labeled energy. It's tough to see, but the y-axis here is labeled energy. And what happens in an exothermic reaction is the reactants have a certain amount of energy. Now, there's no numbers on this particular graph because for every chemical reaction, every exothermic reaction, the amount of energy of the reactants is different for what it's beginning with. But you take whatever that level is, and then you'll see that the graph goes up. Now, it takes energy in order to break the bonds. So in a chemical reaction, there are bonds, and those bonds need to be broken, and then they need to be recombined. And the energy that it takes to break those bonds to start the reaction is what's known as the activation energy. And so this tip right here of the curve is that activation energy. An example of an exothermic reaction is fire. And I like to use fire as a great example of an exothermic reaction. So imagine lighting or striking a match. You're going to create a chemical reaction by striking that match. But when you strike the match, it takes a little bit of energy that you have to input into it to create enough friction, enough energy in order for that match to light. And the point where that match lights is right here at the top of the curve. That's where the energy reaction begins. The same thing with starting a fire. You can't just light something and have that fire start right away. It takes a little bit of energy for that fire to get started. That's the activation energy. Now, continuing on in this reaction, you will see then that the amount of energy goes down and the products end up having less energy than what the reactants have. And that is because heat is released. And so if this line here were to indicate the amount of energy that the reactants originally have, we would, when we interpret this graph, we would take the delta or the difference between this line and the amount of energy of the products, and that's the amount of energy that was released. Because we learned about the law of conservation of mass, there's also a law of conservation of energy, and that says energy is neither created or destroyed in chemical reactions. So the total amount of energy in chemical reactions must be the same. And so we account for that energy by saying this is the amount of energy that was released into the surroundings or into the environment. And since in an exothermic reaction, energy is released into the surroundings, into the environment, that energy is going to feel warm. So if the reaction is happening inside of a test tube, that test tube is going to feel warm. Fire, again, another great example of an exothermic reaction, fire feels warm. And so we go up next to a campfire and warm our hands by a campfire because fires feel warm, and fire is a great example of an exothermic reaction. Again, here on the second slide, exo refers to out, and for an exothermic reaction, we will write energy with the products. So if you look down here at the very bottom, it says reactants, and it's got the arrow and it says products plus energy. And so we will write that energy so that the total amount of energy on the left is equal to the amount of energy on the right. And so the amount of energy of the reactants is equal to the amount of products plus that amount of energy that was released. The second type of energy reaction is an endothermic reaction. And again, we have thermic, therm, and ic, pertaining to heat energy. Endo, that prefix endo, means going in. Think of an entrance. We, meaning people and mammals, we have what's known as an endoskeleton. Our skeleton, our bones are on the inside. Whereas you think about an insect, they have ants and bees and grasshoppers. They have what's known as an exoskeleton. Their skeleton is on the outside. So exo refers to outside, endo refers to inside. And when you go through an entrance, you go into a building. An endothermic reaction is a reaction in which energy is going to go into the system. Now, where does it come from? Well, that energy, because energy is neither created or destroyed in chemical reactions, so for it to absorb energy or energy to go into the system, it must come from the surroundings. And so what happens is that it takes heat energy from the surroundings. Now, if it's happening in a test tube and that test tube is in your hand and you're holding that test tube and you're feeling it, if it's taking that energy from the surroundings, then the surroundings is going to feel cold because it reduced energy from the surroundings. So this is the one that's kind of confusing because we say heat energy is absorbed. And when it absorbs energy, it feels cold because it took it from the surroundings. Now, think of a bucket full of water. And if I had a sponge and I put a sponge into the bucket of water and the sponge absorbed water, and then we removed the sponge from the bucket, does the bucket have more or less water? It's going to have less water because the sponge absorbed some of that water. It took that water from the bucket. Just like in an endothermic reaction, it takes that heat energy from the surroundings. Okay. And since the bucket has less water, the surroundings have less heat energy, and that's why the surroundings feel cold. So an endothermic reaction is a reaction in which energy is absorbed during the reaction. The products will have more energy than the reactants. So when we look at this graph once again, this line again is starting right here, and I put it here in the middle to indicate once again it's the amount of energy that those reactants are starting with. We don't have numbers that go with that are associated with it because every reaction is different. The amounts of the reactants that we have in each reaction is going to be different. But for each reaction, it's going to be a similar pattern. Once again, you'll see this curve goes to the very top, which is the activation energy. It's the energy that's required to get the reaction started. But then you will see that the products, this line is now greater than the reactants. And the difference between the original line of energy and the new line of energy is the heat that was absorbed. So endo refers to going in, and in endothermic reaction, the energy is written on the product side, on the reactant side of the equation. So here we see reactants plus energy to get to the products. So the products have more energy. So to follow the law of conservation of energy, the reactants plus that energy have to equal the total energy of the products. Now, when you go through your slideshow, you're going to fill in these 3 paragraphs from the word bank that I have here. I want to switch screens here. This is a reading that you'll do later on. And you will see these 2 reactions drawn here once again in an endothermic reaction. We start here, we go up for the activation energy, and then we come down, and heat energy is absorbed. And in an exothermic reaction, we start at the amount of energy that the reactants start with. It goes up for the activation energy, and then heat is released. And so that is energy reactions.